Hi everyone, this is Anushka and welcome back to my channel in Economist. So in today's video, we are going to discuss about a very interesting statistical test which is known as the Chow test, right? So the agenda will be to discuss why we need Chow test in the first place. Then we will go into the mechanism, the step-by-step process, how we conduct this Chow test. And finally, we will demonstrate this idea using the help of a sample dataset, right? So this is the agenda. As you can see, Chow test is a test for the structural stability of the parameters. So we'll understand what this structural stability means in details. So let's get started with that. So in the introduction, I have mentioned that when we use a regression model using time series data, so we are considering a variable over a period of time, say from 2000 to say 2025. So over a period of time, when you analyze the variation of a data, that is the time series data basically, it may happen that there is a structural change in the relationship between the regressand and the regressor. Regressand means the outcome variable basically, and regressor is the x variable or the explanatory variable. So, for example, suppose that from 2000 to say 2008, the variation is something like this. Suppose the variation is something like this, but after this 2008 time period, the slope or the intercept of this regression model completely changes. So there is a structural break at this particular case, right? So we know that in 2008 the world has gone through a financial crisis. So that is one of the examples. I'll come to that in which scenario the structural change might happen. So what happens is that when you are considering a time series data, that is, you are observing the variation of a variable over the period of time, what happens is that there could be some situations, some shocks, basically, some exogenous shocks can be there for which the direction of your regression equation might change. Whether it can be either the change in the intercept values or it can be change in the slope values basically. So for example, suppose for some period the regression model is like this. For example, I'm saying suppose 2xt plus some ut. Suppose this is the regression model before say 2008. Before say 2008. This is just an example. But after 2008, what you see is that the intercept remains the same, but the slope changes significantly. Suppose it becomes 10 now. It can happen, right? It can happen. So let me take another error term. Suppose this is the situation. If this is the scenario, the intercept remains the same, but the slope changes significantly. I hope you can observe this from this example. And the similar thing can happen for the intercept term also. The slope remains the same, but the intercept term changes significantly. Or it can be that both changes. Both can also change. So either the intercept or the slope, or both the intercept and the slope terms, if they change significantly. So it basically means in order to model the situation over the period of time, in order to you know establish the variation of the variable, we need two different regression equations, right? Can you observe this fact? If there is a structural change, if there exists a structural change, then we need two different regression equations in order to model this particular structural change. But if there is no, structural change, then a single regression equation will do. So this notion will also help you to, formalize the test that we will discuss in a while, right? I hope this much is understood. Now see, what is a structural change? Here I have said that structural change means values of the parameters do not remain the same throughout the entire time period. If you see this example, the value of the parameters. So structural change means the value of the parameters are changing. That is why, see, here I have mentioned a test for structural stability of the parameters. Structural stability of what? Structural stability of the parameters. That is why we are saying the parameter values are changing basically, right? Due to some sort of intervention, due to some sort of policy, or due to some sort of external shock, what happens is that the parameters are getting affected. And that is the reason why we need two different equations to model the entire scenario. That is when we will say structural change has taken place. And they change after a certain point of time due to certain external causes. What could be the external causes? Like policy changes by the government. It can be due to external exogenous shocks, or it can be different varieties of reasons. Now, how do you model this scenario? If you have this structural break present or not, if you want to, you are trying to detect basically if the structural change is present or not in your model, then you will use the mathematical test known as the Chow test. So, Chow test is a method to find out whether in a given time series data structural change has happened or not. So, the mechanism will be same. We will test whether we need two different regression equation or a single regression equation is sufficient enough, right? So if you test that, that will only give us an idea whether there exists a structural break in our sample data or not. I hope this notion is absolutely clear to you. Now let us go into some specific examples where we can see the structural break. For example, donations given to organization before and after a natural disaster. So here the natural disaster will act as a shock, basically, external shock. So suppose the donation was like this. It is very low initially. After the natural disaster, the amount of donations completely spiked, right? So it has increased significantly. If this is the case, then also you need to have two different regression equation to model this scenario. I hope you can understand this thing clearly. Second example, which I have given you, house prices before and after a significant change in the interest rate. So there have to be some policy intervention or some natural disaster or some sort of external shock, which will result in this two different regression equations, right? So there should be an external thing. There should be an external intervention. That is the reason why we will have two different equation. So one will be before situation and one will be after situation. So when you have this before after scenario, you need to have two different regression equation, and to test that we need Chow test. And the most important example in recent time is the COVID-19 pandemic, that the asset and stock prices before and after a war or a natural calamity like COVID-19 pandemic, that is also a very good example of structural break, right? I hope this much is absolutely understood. This is the concept. Now let us go into the mechanism and understand step by step how would you perform this test, mechanism of the test. So for that, we need to divide the time series data into two different parts. Suppose you have n number of total observation. In your sample, you have n number of observation. So what you will do, you will firstly divide your data set into two parts. First will be N1 observation, and in the second group, you will have N2 observation. So the first observation will be C in part one before the suspected point of structural change and one after the suspected point of structural change. So this N1 observation you will see before the structural change. And N2, you will say it is after the structural change. You will have these two groups. So total N1 plus N2 should be equals to N. This is very evident. So there be N1 observation in the first part, N2 observation is there in the second part. And suppose this is the original regression equation. This is the original simple two variable regression equation. This is the regressand, that is the output variable, and this is the explanatory variable, or it is also known as regressor. So we have two different parameters that we need to estimate, alpha 1 and alpha 2. So what we are trying to do, we are trying to see whether this single equation is enough or not, whether this single original regression equation is enough or not to model the entire, to model the entire variation of the output variable, or we need two different regression equations depending on the values of the structural parameters. So for that, what we do, estimate the above equation if there is no structural change and obtain RSS of R. This suffix R represents the restricted model. So the first step would be what? Take this original model and simply take the original model and simply apply OLS. Simply apply the OLS method over all the observation that you have before dividing this into N1 and N2. All the sample data that you have, all the sample observations that you have, keeping in mind all the data point, you will use the OLS method to estimate the original regression. This is the first thing. And from that regression, you will get the RSS, which is known as the RSS of the restricted model. So the original model is the restricted model. What is the restriction? The restriction is that we are saying that we do not need two different models. That is the parameters, the structural parameters will be a unique parameter. There should not be two different structural parameters. So we need only one single equation. That is the restriction here. We are assuming that there is no structural break. If we are sticking with the original equation, we are restricting ourselves in assuming that there is no need for two different regression equation. That is, only a unique estimations will do. Only a single estimation of the parameters will do, and we do not need any other regression equation. That is the restriction. So basically, we are doing a pooled OLS regression. Basically, pool means we are taking into account all the data points, and then we are running the OLS regression. And from there, you will get the restricted models RSS, that is the residual sums. I hope this first step is, absolutely understandable. We are carrying out a pooled OLS regression, keeping in mind all the n data points that we have in our model. Now, the question is, what will be the degrees of freedom? The degrees of freedom will be like this: n1 plus n2 minus k. See, n1, so we have divided the entire data set into two different groups basically. N1 is the first group, N2 is the second group. So basically N minus K. It is N1 plus N2 minus K means N minus K, where K is the total number of parameters to be estimated. Here in our model, we have only two parameters, alpha 1 and alpha 2. That is why the K value will be 2 short. And this is called the restricted sum of square, the residual sum of square from the restricted model. As I've told you, why this is restricted? Because it relies on the assumption that this is the only structural equation that we need, and there cannot be any other structural equation. That is, we do not need two different structural equations to model the entire scenario, and only one original structural equation will do. And using the OLS, the parameter values that you will get. So you'll get one estimation of alpha 1 cap and alpha 2 cap. So this is the only estimation that we need. This is the only structural parameters that we need. And these structural parameters are stable. They are stable in nature. Stable means that we do not need to change them. We do not need to separate structural parameters. Only this, parameter estimation will be good enough. That is why it is the restricted model, and the residual sum of square that we will calculate from this is known as the restricted sum of square from the residual model. So from the restricted model, right? So this is the first step. Now, what you will do in the step 2C, let the regression equation in the presence of the structural break. Now, what we will do, we will use our N1 and N2 observation. So, suppose this is the first regression equation before the structural change, and this is the regression equation after the structural change. So, see, here the coefficients, the parameters are varying. In the first equation, this is beta 1, beta 2. In the second equation, this is gamma 1, gamma 2. Now, we are assuming that we need two different regression models. As I've told you, to understand the break, you need two different regression equation basically. If we assume that structural break is present, then we have these two different observations. So this is called period 1 before observations. This is period 2. Now what we will do, depending on the N1 observation that we have assumed we have for the before period, we will estimate the first model. See, estimate the first model. And what will be the degrees of freedom? It will be n1 minus k. Here again, k is 2 because beta 1 and beta 2 are the only parameters that we have. So in the first model, the degrees of freedom will be n1 minus 2, basically n1 minus 2. In the second model, we will again do the estimation here. Depending on the n2 observations that we have, degrees of freedom will be n2 minus 2. See? So this is the process. This is step 2. And from these two models, we will again get some residual sum of square. Here we will get RSS1, here we will get RSS2. See, RSS1 and RSS2. Now to find out the RSS of the unrestricted model. Unrestricted means we need two different regression equations. A single regression equation will not do. If you use a single structural equation, that will be restricted equation. And unrestricted means, here see the suffix is unrestricted. Unrestricted means we need two different regression equation, which is the case here. How do you find that out? Simply take the summation. So you have found out what is RSS for the first equation, RSS from the second regression equation. Simply take the sum, you will get the RSS of the unrestricted equation. What is the degrees of freedom? N1 plus N2 minus E. Now you have both the RSS. RSS of the restricted model you have got in the first place. RSS of the unrestricted you have also got from the second step. Now what you will do? We have to form the test statistic. Test statistic will be if statistic. We have to rely on the if statistic. See here, what is the formula? RSS R minus RSS, I mean the RSS of the restricted model minus RSS of the unrestricted model upon K upon RSS of the unrestricted upon N1 plus N2 minus 2K. So this is the entire formula which I have written. And this under H naught follows F distribution with degrees of freedom K upon this. So we know if F distribution, so we'll have here we will have something upon K, and here we will have something upon the values N1 plus N2 minus 2K. So what will be the degrees of freedom? Degrees of freedom will be this upon this and this basically. This will follow F distribution with K and N1 plus N2 minus 2K, degrees of freedom. The numerator and denominator will give you the degrees of freedom of the F statistic. So here, what is the null hypothesis? Null hypothesis is that there is no structural break. Null hypothesis is that there is no structural break. That is, we need the first estimated model is the good estimated model. Basically, there is only one structural equation that we need, that we will obtain in the step one only. That is the assumption in the null hypothesis. Alternative will be we have structural break. If we see that this F statistic is significant, if F is significant, it will imply that we have to go with the alternative hypothesis, which means structural break is present and we need these two different regression equations to model the scenario. And that is what I have written here. Hence, we do not reject null hypothesis. The parameters stability if the computed F values does not exceed the critical value of the given regression. So F distribution is something like this. F is like this. So here you will have the critical value of F. If the statistic value falls in this region, you will reject the null hypothesis and you will say that structural break is present, because you will go with the alternative. You will say, yes, structural break is present in our system. And if your, values, if your computed value falls somewhere here, you will say we are in the acceptance zone. We are in the acceptance zone, and we will say we fail to reject the null hypothesis and we will say there is no structural break. And that is how you will go with the decision two. Now there is a special condition. There is a special condition which is like this. If N2 is less than K, if the after variables are not enough. So it suppose you have COVID-19 pandemic in the year 2020 and you are carrying out the test for 2021. In that scenario, you do not have much variables, right? Observations need some time to form, right? So if you have lesser number of observations than the number of parameters that you want to estimate, if this is the case, then there will be a slight modification if your F statistic. Instead of 2K, you will write or -1. Only this much will be the modification. You can take a look at the comparison. This is the original scenario. N1 plus N2 minus 2K. See, only the denominator is slightly different. Here, instead of 2K, what you will do? N1 minus K minus 1. This is the only modification that you need. Only for a special case when N2, you will see number of observations that you have in the after scenario, after the structural break or after the policy intervention, that is lesser than the total number of parameters that you want to estimate. All the rest of the things will remain the same. Here I have written, see, RSS is the residual sum of square with N1 plus N2 observations, and RSS1 is the residual sum of square with N1 observations, right? So this is about the mechanism that we need to follow. Now I have given you a hypothetical example that will help you to see, basically demonstrate how these things work in real life scenarios. So I have taken a very simplified example and a very small data set just to show you the idea of whatever things I have discussed so far. See here that suppose we have the data on the relationship between advertising expenditure and sales of a product, right? Advertising expenditure and sales of a product over two time points. So basically, sales depends on the advertising expenditure. Sale is the output variable, basically. Y is the sales. Y is the sales at the time point. Suppose the model is like this, alpha 1 plus alpha 2. XT is the expenditure, advertising expenditure plus some duty. This is the original model. YT is the sales of the product. Sales depends on the advertising expenditure. This structural relationship is given to us. Now, over two time points, over two time periods where before and after a marketing campaign. Suppose a marketing campaign is being, run. Marketing campaign is being initiated. Then we want to determine if the relationship between advertising expenditure and sales changed significantly after the marketing campaign. So we want to know what is the impact of this marketing campaign. Whether before and after the marketing campaign also we can use the same structural equation, or we need two different structural equation, whether the sale has gone up rapidly. Before the advertising campaign, the sale was come down. It was following a negative trend. After the campaign, suppose after the campaign, it has gone up. If this is the case, we need two different structural equation to model this scenario. So we want to basically test what will be the impact of this marketing campaign. After the marketing campaign, what we see as a result. That is what we want to test using the Chow test. So we will perform the Chow test to see if there is a significant difference in the relationship between advertising expenditure and sales before and after the marketing campaign, and the sample data is given here. So now let us see the data set that I have given you. This is a completely random, simplified data set. Only 10 observations are here. See, here we have the time period. This is before the marketing campaign. The first 5 observations will be before the marketing campaign was initiated. And see here, the advertising expenditure is denoted by the variable X and sales is denoted by variable Y. And all these things comes under N1. N1, because see, N1 means in N1 you have 5 different observations. N1 means before the marketing campaign, and N2 means after the campaign, basically. So these five observations come under N1. These are the data points that we have as the N1. And next, in the after scenario, after the marketing campaign has carried out, these are the N2 observations. See, here you have after. So altogether, N will be 10. N will be 10, where N1 equals to 5, N2 equals to 5. So altogether we have, if you take the sum, you have 10 different observation, and we want to know whether a single structural equation is capable of modeling this scenario or not, or we need two different regression equations, right? So how do you do that? So first step, see here, the steps I have written down. Here are the following steps. Estimate two separate regression model, as I've told you. For before you will have a separate regression, for after you will have a separate regression. Then compute the sum of squares of the residuals for each regression. So basically, you will compute RSS1 from the first equation, RSS2 from the second equation. We will take the sum to find out RSS of the unrestricted model. If you have two different equations, which means that we have the unrestricted. If you take the sum, you will have RSS1 plus RSS2 will give you the RSS of unrestricted model. Compute the Chow test statistic using the formula mentioned in the earlier slide. So firstly, we have a complete regression equation. We will perform OLS to get the original structural equation. And then you will have this before and after two different regression to compute the RSS of the unrestricted. And then we will apply the formula that we have discussed. Now I have done this entire thing in the Excel, in the MS Excel. You can use any software. Every software have features to perform this Chow test. For simplicity, since it is only regression, carrying out regression, I will use Excel for that. So if you see here, running the regression for only the time point before the marketing campaign. So for before we have 5 observations. See here, you can see it here. I hope this is visible to you. So see here, we have 5 different observations, and this is the entire regression output that you will get. Entire regression output that you will get in MS Excel. Now, what is the information that we need? What we need is the residual sum of square, and this residual sum of square is here. I hope this is visible to you. We have 40. See, here you have residual. Residual sum of square. Here it is 40, and the corresponding degree of freedom is 3. Only this much information we need. So it basically tells you RSS1 will be equals to 40, and the corresponding degrees of freedom that you have is 3, which is very evident because this is basically N1 minus K. N1 is 5, K is 2, so this will be altogether 3. So this degrees of freedom, you don't need any table to compute that, but this RSS you will get from the computed value. And all the other information, all the other stuffs are also given to you. You can take a look at this. And the similar thing you have to do for the after equation also. Here I have written RSS1 is 40 with 3 degrees of freedom. Then we will go into the after regression. See, after regression also I have done the same thing. This is the after regression after the marketing campaign, that is taking into account N2 observations. 5 different observations. Again, you have to see the residual sum of square. This is the residual sum of square. Again, the degrees of freedom is 3. Again, the RSS is 40. RSS2 is coming out to be 40. The degrees of freedom is 3. Now you have RSS1 and RSS2, you can take the sum to get the RSS of the unrestricted model. What will be the degrees of freedom? N1 plus N2 minus K. N1 is 5, N2 is 5, minus 2, which will be 8. 8 is the degrees of freedom. Now we have to calculate the RSS of the restricted model. That is, we have to carry out the pooled OLS regression. We estimate the original regression model, assuming there is no structural change. The result will be obtained from running the regression in MS Excel or any other software that we have shown follows as follows. This is the regression output. As you can see here, this is the residual, this is the sum of square. Residual sum of square is this. And the degrees of freedom is 8, as I have told you. Let me show you the actual figure. I have written this for you. This is the RSS of the restricted model, depending on the data set that we have used, up to 3 decimal places. Now you have to compute the F statistics. So the formula I have already given you in the previous slides. If you put the values, you will get this will be the value. You can do it in your free time. I'm not showing the calculation. Simple, division and subtraction kind of a thing. This is the F statistic value that you will find out. So this is the F computed value. This is the F computed. See here, this is the F computed. And what is the F critical value? F critical value will be this. You can follow the F table. See, this will be F with 2 and 6 degrees of freedom in the numerator and denominator respectively. So let me go back and show you what was the degrees of freedom. See here. So in the numerator, you have k. So k will be 2. And here you have n1 plus n2 minus 2k. So n1 is 5, n2 is 5 minus 2 into k. So 10 minus 4, that will be 6. So in the denominator, you have 6. In the numerator, you have 2. K is the total number of parameters that you have estimated. So it will be F distribution with 2 and 6 degrees of freedom. That is what I have written here. Let me come down and see. Yes. So with 2 and 6 degrees of freedom in the numerator and denominator respectively. Now from the F table that you have in the statistics books, you will have the critical F value at 5% level of significance. If you compute, this will come out to be the critical value of it. You can consult your statistics books, you will see this. So if critical value is less than the computed value, what does this mean? See, this is the critical value. If critical value is something 5.14. And what is the computed value? It's way in the rejection region. 631.516. It's in the absolutely in the rejection region. So rejection region means we have to reject the null hypothesis. See, we have to reject the null hypothesis of the parameter stability. As I've told you, in the null hypothesis, we assume there is no structural break. But here, since we are rejecting null hypothesis, that is, we are accepting the alternative hypothesis, which will conclude that there has been a structural change in the given data. So which means that only one structural equation is not sufficient in order to model this scenario, and you need two different regression models. Two different regression models, and what will be the parameter estimation that will be given by the model. That will be given by this regression output. See here, the intercept coefficient has been estimated here. The slope coefficient is also estimated here. This is for the after scenario, and for the before scenario also you will have this estimation. Everything, the regression output will be shown by the regression output itself. You can check that out from the any software that you use. You will get this. Right? I hope you have got the concept of how to perform this Chow test. And the final thing that I wanted to show you is the drawback. What is the drawback of this kind of test? The main drawback of Chow test is that it only tells us that the two estimated regression equation are significantly different or not, without telling whether the difference is on the account of only the intercept terms or only in the slope terms or the both. So we started off with the question whether we need two different structural equations or a single structural equation is fine. So that question we can answer using the Chow test. But Chow test fails to tell us whether this difference arises due to only the change in intercept or only the change in slope or the both. So from the using the Chow test, you can only tell this much, that whether we need only one structural equation or two different structural equation, but you cannot tell whether the difference comes from only the change in the intercept or the change in the slope or change in both the intercept and slope terms. Right? So this is the main drawback. So what we have seen is that firstly, you have to execute the pooled OLS. You have to estimate the original model. From that, you will get RSS of the restricted model. Now, the second step would be to run two different regression equation before and after scenario. From that, you will get two different RSS. You will take the sum of the RSS. RSS1 plus RSS2 will take the sum. From that, you will get RSS of the unrestricted model. Third step would be to compute the F statistic, the formula I have shown you. For two different cases, the original statistic value I have given you. Also, if N2 is less than K, what will be the value? That also I have given you. So, you'll compute the F statistic value, F statistic value with respective degrees of freedom, and then you will compare it with the critical value, F critical value, and that will help us to take the decision, right? So this is the simple criteria that you have to follow. These are the simple steps that you have to follow. I hope you like the demonstration. And if you have any questions anywhere, please let me know. And in the next video, we'll go into some different topic. And as of now, if you have any questions from this video, please post me down below in the comment section. I'll be more than happy to reply to that. And don't forget to like this video and subscribe to this channel, An Economist, because this gives me immense motivation to continue making such useful videos for you. It takes immense time and effort to make a single lecture video, and I have to do this for 2 to 3 times in a single week in my busy schedule. So if you find these videos are helpful and it is helping you to grasping this concept better, then please support my endeavor and show your love and support towards my channel. This will help my channel to grow, and this will also motivate me to continue making such useful videos for you, right? So thank you so much for your time, and let's meet you in the next video.